In this video, I'm going to explain that how size of quantum dots affects the optoelectronic properties. Optoelectronic properties mean optical properties and electronic properties. As we can see that this is a bulk material and all these four are quantum dots. Before going to detail, let's know a little bit about what is quantum dots. We know quantum dots are semiconductor. It is not metal nor insulator. It is between the metal and insulators. Quantum dots are basically very small. It is in the range of 2 to 10 nanometer. Quantum dots have two specialties. One is the optical property and another is the electronic properties. Both these optical and electronic properties are significantly dependent on the size of the quantum dot and shape. So in this video, I am going to only talk about the shape, right? This is a bulk material of any kind. If you say that cadmium telluride or zinc oxide or titania, tin oxide, perovskite, any kind of bulk material. Here is a billion trillion atoms, right? We know that the band structure of the bulk material is something like this. This is the conduction band and this is the valence band. We know valence band is filled with electron and conduction band is empty. This is another story how bands are formed. This is some called bonding. When there is a bonding, the valence band form, and when there is anti-bonding, so the conduction band is formed, right? This is very easy theory. Now this band gap play a very important role here. The question is now, when we decrease the size, so the band gap increases. When the band gap increases, we know this very famous equation. When the band gap increases, the wavelength get decreases. When the wavelength get decreases, we use high energy photons because the energy equation is H is equal to H C by lambda. So for instance, if we have a shorter wavelength, we will utilize high energy photons. And what the high energy photons basically doing, it multi-excitons. It generate multi-excitons. It means that with one photon, we can generate few electrons, electron holes. Exciton is basically nothing but it's the combination of electron and hole. This is called exciton. So with high energy photon, we can generate multi-excitons. This is how when we decrease the size, so we increase the band gap, and when we increase the band gap, basically we shorter the wavelength, and when we shorter the wavelength, we know electromagnetic radiation, so we need high energy photons. Shorter wavelength contains high energy photons, right? Because the frequency in wavelength are inversely proportional. So when the wavelength is increasing, so we get lower energy photons, and when the wavelength is shorter, we get high energy photons, right? So for instance, look this band gap. If we look into the 8 nanometer quantum dot, this is basically the band gap, right? When we further decrease the quantum dot, so the band gap increases here. What basically, the conduction band is also moving positively or negatively, and the valence band is also moving downward. Now look, I will explain this very well. When we further decrease the size here to 4 nanometer and further 2 nanometer, the further we increase the band gap. Why? Because it is very simple theory that in this case, more electrons are occupied in this area here, and when we excite the electron, so more holes are here and more electrons are there. So the electron occupy more space, let's suppose. When we further decrease the size here, so here we have less holes and we have less electrons here. So electron occupy less space. So this band basically move forward and this move downward. So it increase the gap between the electron and holes. And similarly here, this is very easy theory. Now, basically, what is the benefits here, that if we have this quantum dot, 12 nanometer, 10 nanometer, and 6 and 2. So what basically, it's shifting this peak toward blue here. This means that if we decrease the size, so we get high energy photons, because look, the wavelength is increasing in this direction here, and if we have smaller quantum dots, so there we have quantum confinement effects. This means that we shift the peak toward high energy, and high energy means the blue light, right? So it also play a very important role in fluorescent materials, that if you have one material and you want to emit blue light, so you decrease the size. Very simple. For instance, if you are looking for a fluorescent material which emit blue light, or if you are interested in green light, and if you don't have the kind of material are expensive, just take any material and decrease the size of that material, so you will get the green or blue light. This is how important are quantum dots, how beneficial, and there are so much application of quantum dots, right? And these equations also play a very important role again here, same equation, right? As I explained that the optoelectronic properties depend on size here a lot. For example, we explained that if we have larger quantum dots, it emits longer. This basically simply means that the size is basically directly proportional to the wavelength. If we have large quantum dots, large wavelength. Large wavelength means small energy, small band gap. You see here, large quantum dot mean large wavelength and small band gap. You see, band gap is increasing here. You see here, small quantum dot, small mean small wavelength. Small wavelength mean high energy. The blue one here, you see here, this is the reverse. The graph is here reverse basically of this one, right? So this is how we tune, we manipulate the properties of a material using the size concept. That when we decrease the size, we can tremendously improve or tune and manipulate the properties of the material. So it play a very important role in photovoltaics and means solar cells technology, that if we want to absorb some high energy photons and maximize the efficiency. And also it also play a role in photoluminescence, for example, fluorescence material.